All right, so in this video, I want to talk about um, a rule in calculus called L'Hopital's rule, or you want to say that L hospital. I know you want to say that. If you're um, somebody who does not speak French as a native language, but it's L'Hopital's rule. I will say that it was another way to write it is L Hopital's rule. L, it looks like hospitals rule. And that's actually how I first learned it whenever I was taking calculus. That's how I remember them telling me. So anyhow. So just for even for a little bit of very, very brief context, L'Hopital was apparently a mathematician, a French mathematician back in the 1600s. He was credited with finding this particular rule out that we're going to talk about here, but it wasn't him. It was apparently this rule was more so associated with a man whose name was Bernoulli, Johann Bernoulli. Um, but yeah, anyway, these people, it's amazing to me. These people were mathematicians and they spent all of their time essentially researching and learning different ways, different concepts of math, solving different type of problems and stuff like that. For us, it seems kind of boring, unless you're somebody who really, really enjoys that kind of stuff. But anyway, I just find that kind of stuff pretty fascinating. But anyhow, I digress because I'm about to go off on a tangent and I can even feel it. Let's go ahead and talk about L'Hopital's rule. So this is a rule in calculus that basically says the following. So I'm going to write this down first and then explain. Okay. So you have df dx when x is equal to c, and then dg dx when x equals c. All right. So what in the world does this mean? Basically, okay, and I see I left off the c here. Basically, L'Hopital's rule says when you are trying to find the limit of the ratio of two functions, you see the ratio of f of x to g of x, and either one, each function, the limit of each function approaches zero. So you have like this type of situation as x approaches c, or scenario number two, the limit of each function approaches infinity, or put a proper r there, negative infinity. This rule applies because and this is what's called like an indeterminate type of situation. Basically, you can't have like zero in the denominator, so because everything kind of blows up from there. And then also having a situation where you have infinity over infinity, you can have like 1 over infinity, you can even have infinity over a number. But to have infinity over infinity or a negative infinity over a negative infinity, basically, how do you find the limit of that? You see what I'm saying? You can't necessarily say infinity divided by infinity is 1. It's just not enough information to be able to determine that. However, if you have any of these situations, basically the limit is going to be equal to the derivative of the top function at x equals c over the derivative of the bottom function at x is equal to c. This is a way that you can essentially find what the limit of a ratio of functions is when you have either of these two situations. Now, we're going to start with an example that I did whenever I talked about finding the following. So we talked in a previous video about how to find the following limit. So in a previous video, we proved that the limit as x approaches 0 of sine of x over x is equal to 1. So I'm not going to rehash that. You just need to go back and watch that video to determine that. But so we had to do that by essentially zooming in real close, and we even had to use some geometry, some trig in there and all that kind of stuff. Or even kind of like try to zoom in really, really closely to notice that limit of that sine function over the x function is equal to 1. But L'Hopital's rule is really a way to kind of make this type of thing a lot more simpler to see. So let's apply it, because we know that if we plugged in 0 into this function, you would have a situation where you have 0 over 0, which, can't do it. But now we're going to apply L'Hopital's rule here. Now, let me go ahead and just so I can distinguish for you guys who are going to copy these notes, just kind of put that in its own separate bubble there so you can see it more clearly. So we're going to apply L'Hopital's rule to this classic sine x over x example. So it's going to be equal to the derivative with respect to x of sine of x as x equals 0, or when x equals 0, and then the derivative with respect to x of x when x is equal to 0. Okay, so what's the derivative of sine of x? Derivative of sine is cosine, and then we're going to set that, we're going to say cosine of x at x equals 0. The derivative of x is just 1. And so, there is no x there, so it's not really an x equals 0 type of situation. So the question is, what is the cosine of 0? Stick that 1 there. The cosine of 0, if you remember your unit circle, the cosine of 0 is 1. So that's going to be 1 over 1, or just 1. So you see, and let me say this is example number 1. So you see a much cleaner, faster way to see that the limit as x approaches 0 of sine x over x is equal to 1. Let's do a second example. All right. So we're gonna find the limit as x, and this shows you the value of derivatives, how derivatives come in handy, and just really help to solve math problems that you may have solved other ways, but other ways it might take more lengthy a more lengthy period of time. So we want to find the limit as x approaches 0 of 2x over e to the x minus 1. Now, again, why are we doing this? Because if you were to direct substitute that 0 in, you would have a 0 over 0 situation, because 2 times 0 is 0. Then e to the 0 is 1, and 1 minus 1 is 0. So you have that indeterminate situation. So we're going to use L'Hopital's rule. All right. So that means we're going to take the derivative of the top and the derivative of the bottom. So derivative of 2x is just 2. The derivative of e to the x minus 1, you're going to take the derivative of each separate term. So derivative of e to the x is just e to the x. The derivative of 1 is going to be 0. So this is just going to be e x on the bottom. And we want to find that. So 2 over e to the 0. E to the 0 is just 1. So this limit is just equal to 2. Nice and quick and clean. You see? Even fun. For me, at least. And hopefully for you too. Let me see. I think I have another example I wanted to go over here in my notes. And I kept them. Okay, I have 2 more examples I want to go over here. So let's erase these. Okay. But yeah, this is why calculus is so useful. It kind of like simplifies. It's a simpler way of going about solving certain type of problems. All right, so example number 3, we want to find the limit as x approaches 1 of the natural log of x over x minus 1. Now, again, we can't direct substitute because the natural log of 1, just keep in mind that's what power of e will give you 1. So that would be the natural log of 1 is 0. So you have 0 up here, you have 0 down here. Can't do it. Okay, so we're gonna apply L'Hopital's rule. So that's gonna be the derivative of the top. Derivative of natural log of x is 1 over x. And we're gonna want to find when x is equal to 1. And then the derivative of x minus 1 is just going to be 1 because the derivative of x is 1. The derivative of 1 is just going to be 0. So it's going to be 1 here. So we're going to apply x equals 1. So that's 1 over 1 over 1. So this is 1 over 1, which is just 1. Nice and clean. All right, we're going to do one more example. And I kept all these examples pretty easy just to illustrate it, but obviously it can get pretty a bit more complex from here. Just get the idea here. So the limit as x approaches 4 of x squared minus 16 over x minus 4. Again, if we directly substitute it, you would have 0 over 0. So we're going to apply L'Hopital's rule. So we're going to take the derivative of the top. Okay. Applying the chain rule, the derivative up top is just going to be 2x. The derivative of the bottom is going to be just the derivative of this term, which is going to be 1. Remember, this is going to be 2x at x equals 4. So you're going to have, when you substitute in 4 there, you're going to have 8 over 1, which is 8. Now, it's important to note with this example, though, that you would not have necessarily needed L'Hopital's rule to solve it. Why? Because you have a situation where you could have factored out and then went ahead and substituted in. So let me just show you that real quick. So L'Hopital is a way to solve that, but it's not necessarily the only way you could have solved this one here. So let's see. So the limit, let's rewrite that. The limit as x approaches 4 of x squared minus 16 over x minus 4. So that'd be the limit as x approaches 4. X squared minus 16, that's a difference of squares. That's x plus 4, x minus 4 over x minus 4. You see x minus 4 on the top and bottom cancel out. So you have the limit as x approaches 4 of just x plus 4. So then you can directly substitute that. So it's going to be 4 plus 4, which is equal to 8. And you see these are the same. Okay. So L'Hopital's rule helps you to solve these type of situations where if you took the limit, you would have 0 over 0 or infinity over infinity or negative infinity over infinity. Helps you do it a whole lot faster. All right. Math is really cool. All right. So remember, if you need tutoring, you see the links here. You need SAT, ACT math practice, you see the link there. Don't forget to subscribe to this channel, like, share this video. All right, y'all. Thank you for watching and have a great day.